I'm Michael Zeilnhofer, and I just want to highlight some of my research experience. And I also want to thank you for setting this whole thing up. It's really unique and great to have it, especially because it's virtual under current circumstances. So my undergraduate research experience was conducted at Western Connecticut State University. I did quite a bit of observations on exoplanet transits using Kepler mission data as well as WASP and the HAT-P surveys. I used a 20-inch campus telescope with maximum DL to reduce the data. And then I also did some observations and modeling of close contact binary systems, looking at PS Virginis as being one of those contact binary stars. And I did the observations using the 20-inch campus telescope, and the maximum DL was used to reduce the data. And then I also did some modeling work with these binary stars, looking using Binary Maker 3.0 to look at sunspots, or I should say star spots, and then temperatures, and also the contact envelope between the stars. My graduate research was more in depth, and actually it was a change from what I did in my undergraduate research. So my graduate research was done at Northern Arizona University. I have a master's degree in applied physics and planetary science, and during that time I looked at impact cratering in north central Arabia Terra. I developed a small crater database with about 2,200 craters between 1 and 5 kilometers, looking at several different types of interior morphologies. And I mainly looked for ones that were related to glacial and fluvial activity. I did look at some tectonic features as well as aeolian and complex features. But the reason why I was looking at glacial and fluvial morphologies was to better understand the glacial and fluvial activity that occurred within the region during more recent times, such as the Amazonian time period, and linking it back to the obliquity cycle of Mars and what that can tell us about the current GCMs for Mars. I used ArcGIS to create distribution maps to look at these various features across the surface, as well as constraining ages of the interior morphologies using the crater size frequency distribution plots using Craterstats 2.0. You can go to the next slide, please. Thank you. And then my PhD research was also conducted at Northern Arizona University. So I developed a crater database for Ceres containing about 44,594 craters greater than or 1 kilometer in diameter. This database contains a variety of information, including latitude, longitude, crater diameter, interior morphologies, ejecta blanket morphologies, crater depth, crater rim height. And from this database, I was able to investigate interior morphology such as central peaks, central pits, bright and dark albedo features, lobate flow features. And this was all to so I could make a pretty much a planetary comparison to further understand Ceres crustal properties, since Ceres is such an interesting object. And then I also developed a polygonal crater database. And this polygonal crater database is more comprehensive than some of the smaller databases that are out there right now, due to the fact that I was looking at the number of sides for these polygonal craters, angle between linear rim segments or sides, as well as the relationship to fracture systems seen across Ceres, and subsurface fractures, which didn't break through the surface, and what that can tell us about any weakening mechanisms and how it may relate back to Ceres' true polar wander. And I also did a planetary comparison for Ceres and its polygonal impact craters and to other solar system bodies, just so that I can see how polygonal craters formed on Ceres and how it differs from these other bodies. I also used ArcGIS to look for regional trends. I investigated the depth diameter relationship, as well as the simple to complex transition diameter for Ceres. And I conducted regional analysis, looking at latitudinal zones, as well as investigating global and regional ages for the crater size frequency distribution using Craterstats 2.0. Next slide. And here's my contact information. Thank you.
Okay, thank you, Michael. Hey, our next up is Jane.
Okay, so hi everyone, my name is Jinghan Peng, you can also call me Jane. I am from the University of Victoria, currently doing a master's degree with Dr. J.J. Cavalier my main interest in Kuiper belt object observation and anything planet-related observation, and my contact info is kind of unseen. But anyways, so, oh, can you click? Okay. Oh, okay. So the object of my research is the Kuiper belt object 2002 and MS4. This is a very interesting object because it has is one of the 10 biggest Kuiper belt objects without a name yet. And the cooler thing is that we observe it on Earth, but we also observe it by spacecraft New Horizon. So by observing it and plotting a phase diagram of it, we can learn about its surface property and therefore comparing it with other objects and therefore learn about the solar system evolution and the relationship to it. So in this diagram, you can see there is a ring, the Kuiper belt, and then I have a fake object 2002 MS4 on the top left. And if you can click again and again, please, thank you, and again. So we can see that New Horizons spacecraft is flying over it, and then we're making a phase diagram plot, which is on the x-axis, the phase angle, which is the angle between the sun, the observer, and the object, so as indicated by the two arrows in the slides. And my main objective is to provide the low phase observation of MS4. If you can go to the next slide. Thank you. And this is a MS4 full phase curve. On the left-hand side is the phase curve provided by CFHT, which is what I mainly do. So I measure accurately the magnitude of MS4 ranging from phase angle 0.3 to 1.2 degree, and then it is fit with the high phase data observed by the New Horizon LORRI camera and provided, and Verbuscher has combined the graph together, and from the phase diagram, we noted that it has a moderate opposition surge, and the slope of the phase curve is pretty flat, which indicates that we might have some special surface property. Yeah, and the measurement on CFHT is at high precision, up to 0.02 magnitude. If you can go to the next slide, please. In addition to that, I also did a MS4 occultation event. If you can click, I hope, yes, the video is going to play. This is the video of the occultation event. And then we look at the circle and then blop, the star is occulted. It is a star of 15.6 magnitude. And then on the right-hand side, it is the light curve of MS4 occultation by the star. And by analyzing the light curve, we noted 36 plus minus 3 seconds of duration, which give us a lower size limit of 635 kilometer and a most likely size estimate of 900 plus minus 70 kilometer. And this size estimate and the R albedo estimate is inconsistent with the Vilnius 2012 result. So yeah, what the work I've done in my master, I really enjoyed it. I'm looking for something observational, Kuiper belt, or planetary, and I really enjoyed computer work. fits. I also worked with megapipe data. Data, and it's been a lot of fun. And if anyone is interested, feel free to contact me at jinghan@uvic.ca. And the information is in my first slide. Yeah.
Okay, thank you, Jane.
Yes.
Okay.
That's my. Thank you.
Xiaochen, very good.
Okay.
Whenever you're ready.
Okay, cool. Thank you. Yeah, so thank you so much for holding this virtual network event, and I really enjoyed it so far. And I'm Xiaochun Mai, currently a PhD student in Washington University in St. Louis, and just defended my thesis on April the 15th. And in my graduate work that I've gained geophysical modeling experience of solar system small bodies in terms of Ceres, Vesta, and Karakostas actually. For Ceres, it's mainly on its gravity and topography. For Vesta and Karakostas, it's basically using a Monte Carlo simulation to study their rotational evolution due to impacts. And then through this work, I'm also get interested in impact processes such as pi-group scaling laws. And for my classwork conducted at graduate school, that I also have experiences in geospatial analysis by using ArcGIS software and spectral modeling by ENVI software. And next slide, please. So just to give you a quick example of my work on a Kuiper belt object, that I've conducted work on a Monte Carlo simulation on Karakostas to investigate its possible spin down histories. So when New Horizons encountered Karakostas, that it sends back the image showing that Karakostas is a binary system. But classical mechanics tells us that when these two lobes are in contact with each other and started to co-rotate with each other, its spin period is consistently smaller than what we have observed. So because I have had a Monte Carlo impact simulation on Ceres, so I basically just adjusted the same Monte Carlo simulation on Karakostas to study how impacts alone would affect Karakostas spin. So I used a dynamically equivalent triaxial ellipsoid as shown on the lower right-hand side of the image to represent the bilobate configuration of Karakostas. And then I chose 100 impacts to collide with this triaxial ellipsoid with various impact velocity distributions and size distribution from the pre-encounter predictions. So I run 5,000 simulations for each Karakostas bulk density that I chose, as shown on the right-hand side, from 300 kilogram per meter cube to 500 kilogram meter cube. That covers a significant amount of porosity on Karakostas actually. So each set of data consists of 5,000 runs, and I plotted them on this box plot. That the red line here is the median value, and box is 25th percentile to 75th percentile. And whisker length is 1.5 times the width of the box. The yellow numbers all indicates how many simulations that has actually ended with Karakostas final spin period that is greater than its observed value today. And as you can see, it has a very clear trend that as the Karakostas bulk density goes down, the final spin period consistently goes up. So that means that basically is due to classical mechanics because of the decrease in the gravitational pull. However, what is interesting to me is even though with Karakostas' lowest presumed density in our model, there are only 1.1% of the simulations that has given us the successful spin down of Karakostas. So this is a very preliminary result, but still from these results, I conclude that even with impacts alone, Karakostas is very unlikely to undergo its successful spin down from a faster spin to its observed value. And this is a manuscript in preparation, and I will surely just expand the simulation and make it more realistic to Erica's, and hopefully to submit that sometime this year. And if you go to next slide, please. And if you are interested in my work and also looking for collaborations, please feel free to contact me by email or mobile phones. Thank you.
All right, thank you, Xiaochen. And up next, we have Terra Tomlinson. Oh, great, there you are. Okay.
Hello.
All right, whenever you're ready, go ahead.
All right, thank you, Andy. Good afternoon, everyone. Like you said, my name is Terra Tomlinson, and I'm a senior undergrad for about 4 more days at the University of Colorado here in Boulder. And today I'm going to talk about my favorite of my research projects, looking at craters on Europa, specifically craters that have unusually dark ejecta. Hopefully this will give you an idea of the kind of things that I'm interested in and experienced in. So, now from what we can tell, there's only about 43 craters on Europa, but about half of them have this darkened ejecta. The other half don't. There's no immediately obvious correlation among the dark ejecta craters, geologically, geographically, they're everywhere. So my goal is to figure out what's darkening the ejecta of just these certain craters, and how does that fit into our overall view of surface geology and geologic processes at Europa. Now, to do this, I started out with a few possible culprits for the darkened ejecta. First, I considered that dark impactors could be responsible. Most of the meteorites that hit Europa are Jupiter family comets, which have an average albedo of about 0.04. So by calculating the mass of a probable impactor from the size of the crater it made, I can get an idea of how much dark material an impactor would contribute to the ejecta. Now, secondly, I wanted to consider any underlying processes that might be causing chemical changes to the ejecta. To do this, I wanted to look at the spectral signatures in and around the ejecta to see if any chemical signatures immediately jumped out as something that could be darkening the ejecta. Thirdly, I noticed that most of these dark ejecta craters have what looks like fluidized ejecta, which makes sense. So by understanding how much melt would be generated in a Europa scale impact, I can compare that to the amount of dark material observed in the ejecta, see if they match up. Of course, to do all this, I first need to know how much dark material is in the ejecta. So I used a radiative transfer model along with crater images from the Galileo spacecraft to do a bit of image analysis and determine what the concentration of dark would need to be to cause the amount of darkening we observe. I also took care to remove any dark material that was already on the surface using albedo data created by Voyager. Next slide, please. Okay, so here are our 3 contenders. First off, let's look at the dark impactor hypothesis. So to find the size of a probable impactor for each crater, I used malicious pi scaling combined with standard impact parameters from Zeilnhofer et al. And I found that in almost every case, the impactor could not contribute nearly enough dark material to match what we see in the ejecta. There's 2 special cases you might notice there. Those are sort of erroneous for this particular method. Happy to talk about why later if you like. My second hypothesis required looking at the spectra of the ejecta to see if there were differences that could account for this darkening. Galileo spectral data is notoriously sparse, so what I was able to extract told me that Europa is, very icy. We see prominent water ice bands with some smaller absorptions for things like magnesium, sodium, iron, nothing that hasn't already been identified from the data before. And these absorptions are fairly consistent across the entire surface. So spectrally, there's really nothing special about this dark ejecta. The third hypothesis I tested was looking at the melt production due to the impact. I used a combination of ICL hydrocode modeling and numerical modeling to simulate a Europa-sized impact and determine how much of that ejecta that was created would be melted. Now, unfortunately, ICL doesn't handle phase transitions in ice very reliably, and compared to the more reliable numerical models, it overestimated the melt by about 2 orders of magnitude. But it did give me some very pretty gifts, and I threw one of those in there. It doesn't look like it's going, and that's kind of sad, but it's all right. But even if we assume that all of the melt produced is darkened, adding that amount to the amount of dark material contributed by the impactor, there still isn't enough dark material to account for what we observe. So it's a step forward, but there still has to be something else going on. Moving forward, I'm looking into some more active surface processes that could be coming into effect after the original impact. Things like ion sputtering, micrometeorite gardening, and thermal segregation. Now, not only could these contribute to albedo changes in our crater ejecta, but it might also tell us about the rates of darkening that are happening and could give us another means of dating the craters on Europa and learning more about Europa's surface in general. Next slide, please. Great, thank you. Thanks very much for coming today. If you'd like to get a hold of me, my contact information is here. I am currently looking for a research position for the upcoming year, so thanks for coming.
Thank you, Terra. And next is Cynthia. Oh, okay, so whenever you're ready.
Okay, great, thank you. Hi everyone, my name is Cynthia. Terra, I share your excitement at graduating soon. I am also an undergraduate at the University of Colorado Boulder, and I'll be presenting my research with Dr. Crow on impact melt inclusions in Apollo 14 zircons. So these melt inclusions are formed through shock heating, which is a process where the pressure from an impact causes localized decompression melting of the minerals surrounding the zircon. And these mineral melts can be trapped inside microfractures inside the zircons themselves. So previously, work has been done on terrestrial zircons at the vertiform impact structure in South Africa, and it found out these melt inclusions are compositionally similar to the surrounding minerals. And so we're applying this technique to the moon. And we want to look at zircons on the moon because they are some of the oldest materials on the moon. A good majority of them are detrital, and they've shown evidence of recording multiple impact events. So they potentially contain a long record of bombardment on the moon. And what we're trying to ask with this project is, do the melt inclusions represent the mineralogy of the current rock that they reside in? Or do they record some other older prior lithologies, which can give us some information about where the zircons formed from? Next slide, please. So for this project, we looked at sample 14311, which has been identified as an impact melt breccia with unusually high volumes of zircons. And so we looked at elemental compositions on 3 scales. So first we looked at bulk rock using micro XRF, and we found about 4 potential different lithologies, which were generally characterized by potassium levels. We then performed quantitative wave dispersive spectroscopy using an electron microprobe to target individual minerals and get a robust representation of mineral compositions in the sample. And then we performed semi-quantitative energy dispersive spectroscopy using a scanning electron microscope for looking at melt inclusions. And then we want to directly compare the mineral and the melt inclusion data that were stoichiometrically similar by graphing them onto mineral diagrams using Origin Pro, and then want to see how they related to each other. Next slide, please. So far we've looked at melt inclusions for 3 zircons. We're currently looking to get about data for about a dozen or so more zircons. So these are just the preliminary results right now. On the left, we have a pyroxene quadrilateral, and on the right, we have the feldspar ternary. The black points represent the melt inclusion data, and all the colorful ones represent the mineral data, which are separated out by the bulk rock lithology that they appear to reside in. And you can see that the melt inclusion and the mineral data align very well, which strengthens the previous conclusions that the melts are sourced from surrounding minerals. Looking at the pyroxenes, the inclusions appear on average a bit more magnesium rich. We didn't get any clinopyroxene-like compositions, so we're not sure yet if that's something that's unique to the shock heating process. And then looking at the feldspar ternary, the inclusions are clustered as being either very calcium-rich and northacidic type compositions, or else being very K-spar-like in composition. And the K-spar-like, we see a bigger spread, and that's not too surprising since on Earth we know that potassium preferentially enters melts. So that spread may just record a wide variety of peak pressure and temperature conditions that are experienced by the zircons. And you also see 2 starry data points. They lie in what we call the feldspar immiscibility gap. They technically shouldn't exist. So we've interpreted this as like a mixed or glassy phase so far. And that is consistent with what Dr. Crow has observed in other Apollo zircons as well. And again, we're in the process of getting more melt inclusion data. And we're trying to fill out these diagrams a bit more and see what range of compositions these impact melts can get. And ultimately, what we're trying to do is synthesize these results with additional information, things like zircon ages, things like constraints on peak pressure and temperature conditions, and then we're trying to put together a general timeline of the impact processes and events that are recorded in these melt inclusions. Next slide, please. So here's my contact information. Huge thank you to my advisor. Huge thank you to LPI for holding this networking event. And yeah, I'll end my presentation here. Thank you all.
Okay. Thank you, Cynthia. And up next, our final presentation for this session from Foivos.
Hello, my name is Phyllis Khare-Acostas. I'm postdoctoral associate at the University of Maryland. And my LPSC poster was focused on the seismic investigation of a meteoroid airburst that happened in Greenland in July 25, 2018, near the city of Kanak, as you can see on the map, which is on the left side of the screen. Next slide, please. So our interest is to understand the properties of an airburst as a seismic source or a source of generation of infrasound waves that can be detected either by microphones or mostly seismometers, which are located on the ground. And as we had this kind of data from Greenland, we try to understand and regenerate the wave propagation. As you can see on the left side of this screen, when the meteoroid is entering the atmosphere of a planet, is generating a ballistic cone due to its supersonic velocity in the atmosphere, due to the friction of its material with the material of the ambient atmosphere. And then if there is a final explosion when this object is totally fragmenting in the atmosphere, we have this kind of generation of shock waves, atmospheric shock waves that can be converted into linear acoustic waves in the atmosphere or generate seismic waves through the coupling of the atmosphere and the solid part. So what you see in the right part of the screen is how the overpressure due to this shock wave in the atmosphere is evolving with the time and the distance that the wave is traveling. So there is some point that this wave is becoming a linear wave. We don't detect the shock wave anymore. In this case, we consider this to happen in about 100 meters far from the source, which is at about 43.3 kilometers of altitude. So we try to understand how the seismic waves that we detect there are generated. And in order to see the seismic waves, we can go with the next slide. And first I have to show you where we detect the seismic wave. So you can see the seismic station of Tuleg indicated with this blue triangle. It's about 40 kilometers south of the location where the final explosion of the meteoroid happened. As you can see on the left part of the screen, on the right part you can see the relative position of the seismic station and the meteoroid. So now we can go and see the data in this last slide. So these data are interesting for some reasons. First of all, we can see a very clear wave front. You can imagine the wave front like a wall that is hitting altogether the seismometer if it's in the atmosphere, or you can consider the same thing in the solid part. Here you can see that in these spectrograms that we have simultaneous detection in very clear, in a very broadband range of frequencies, and a very specific excitation in frequencies that give some kind of resonance during the day. So we try to investigate this with the knowledge that we have our seismometer located on the top of the ice shelf. So by developing some techniques, by developing some techniques that are already applied in preview and validated for previous in previous papers and works for other airburst events, we try to apply the same techniques here in an ice shelf in order to do the inversion of the structure of this ice shelf using the airburst. And all this because in the future we will have missions in worlds where there is a dense atmosphere and places where ice shelf exists, for example, Titan. And my goal in LPC is to drive all this work towards a contribution, for example, the Dragonfly mission. Anyone who is involved with the mission and wants to discuss more, I will be highly interested to meet in the meeting room. Thank you very much.
Hey, thank you. Thank you, Foivos. Okay, so that wraps up this afternoon's session.